Chapter 4. Chapter 4 is about 2D steady state conduction. So, from in the previous chapters, from chapter 1 to 3, we've looked at conduction or convection only in one direction. So, the heat diffusion equation that we had just had a one variable, uh, that's x or y, whichever direction the heat was flowing in. But in this chapter, we'll be looking at heat conduction in a 2D space or in two directions. And there are two approaches of uh, solving the heat diffusion equation in 2D. So before we solve the heat diffusion equation, let's look at how the heat diffusion equation looks like. So our heat diffusion equation will be del square T by del x square plus del square T by del y square equals to 0, assuming that uh, our heat conduction is in x and y direction. If it's in x and z direction, we'll have a z square instead of y square, and if it's in z and y direction, we'll have a z square instead of x square. So uh, here your temperature will be a function of x and y now, instead of just being a function of one variable. So we have our temperature being varying in two dimensions. Now to understand this problem or to solve this equation, there are two approaches based on how complex your problem is or what you know. The first approach is that your equation may have exact solution, or you may be able to solve for exact solutions and then plot a temperature distribution or find the temperature distribution in that particular object or field of interest. And the second approach is finding an approximate solution or using numerical methods. So in some scenarios, it's difficult to get an exact solution. In that case, we distribute our body or domain into small uh, elements or volumes based on what problem you're solving. And then we use a numerical method or an iterative process to calculate the temperature distribution, and we will be looking at that in this chapter as well. In most, if your problem is extremely complex, you may have to use a computer program. You may like you can you'll have to develop a code and apply a numerical method, and you can do that in any of the uh, computer coding languages that you prefer, and or you may even use some commercial codes, but that's not the scope of this class. We will be looking at solving finite element problems. So we will be looking at how to find approximate solutions, but they won't be so complex. And some of them you will be able to do it by hand, but for most of them you may have to use some computer program to solve the system of equations, and we'll look into it as we progress in this chapter. So moving on to our heat diffusion equation, what we do uh, is that we transform the variable t into a normalized variable. So we use a normalized variable, and let's say this variable is phi, and I will define phi as the temperature, the unknown temperature at any location x and y, minus some known temperature at a boundary T1 upon T2 minus T1. And let's take the example of the rectangular plate. So the length of the plate is L, the height or width of the plate is W, T1, the temperatures on the three surfaces is T1 and the temperature on the top surface is T2, and you have y and x direction, and we have to find the temperature distribution, say in this plate. Now, why do we need to normalize the heat diffusion equation? That's because after normalizing, our temperature or our new variable phi will have a range between 0 to 1. So sometimes it is easier to plot or understand a normalized variable or solve an exact solution using a normalized variable. Your boundary conditions simplify, and you will see uh, that as we move forward. Now we will be deriving the exact solution for this particular equation, but you may not have to use it or memorize it, but you should appreciate and understand how the exact solution is derived. So that's why we'll go through it in this video. Okay, so let's see how our equation transforms into. So first let's calculate what our d phi by dx or dy will look like, or let's say this is del phi by del x, and that will be your del of t upon, sorry, your del x into 1 upon t2 minus t1 minus del t1 by del x divided by t2 minus t1, but because t1 is constant, this will be 0, and the only term remaining will be your del t by del x. Similarly, you can do this for your partial derivative in the y direction as well, and see what uh, partial derivatives you get with respect to phi. Now I'll just write the final equation that we get on substituting phi and transforming the equation into the normalized variables. So our new heat diffusion equation will be del square phi by del x square plus del square phi by del y square into, you will have a term of t2 minus t1 in the denominator, oh I'm sorry, in the numerator, equals to 0. Now because we are assuming that there is a temperature difference, your T2 will not be equal to T1, otherwise there won't be any heat transfer. So that means our del square phi by del x square plus del square phi by del y square should be equal to 0, and this is the heat diffusion equation that we will be solving for. Okay, so this is our heat diffusion equation, and in terms of phi, and let's see how our boundary conditions look like in terms of phi as well. So let's define phi first again. So our phi is t minus t1 upon t2 minus t1. This will this will translate to a phi equal to 0 at this boundary, phi equal to 0 at this boundary, and a phi equal to 0 at this boundary. But because t is equal to t2, our phi will be equal to 1 here. So you see that all the boundaries are uh, between 0 to 1, and that's why we've used the normalized variable here instead of t or theta. So moving on, let's find the solution for these equations. Now to find the solution, we'll use the separation of variable approach. So what we do is that we assume that the solution for phi of x comma y is of the form some function x, which is, or some solution x which is just a function of lowercase x, and some function uppercase y which is just a function of lowercase y, and uh, our our solution for phi of x comma y is a combination of capital X and capital Y. So because capital X is just a function of x and capital Y is just a function of y, we can separate these variables. Now let's substitute, let's say this is equation 2 in equation 1, and let's see what we get. So the equation that we get is minus 1 upon x into d square x by dx square. Now because our uppercase x is just a function of one variable and not a function of two variables, our partial differential equations convert into ordinary differential equations, and this will be equal to 1 over y, capital Y. This is a function of x, and this will be a function of y into d square of y by dy square. Now let's say that we introduce a new constant called as the separation constant, and let's say that this equation is equal to some positive constant lambda square, and we've taken it as lambda square so that we get a positive value on the right hand side, and you will see uh, why we've taken it as lambda square and not lambda as we move forward. So now we can write equation 3 into two equations. So our first equation will be d square x by dx square plus lambda square into x equals to 0. So let's say this is equation A, and our next equation will be d square y upon dy square minus lambda square y equals to 0, and let's say this is equation B. Okay, so now because we have separated the heat diffusion equations into two second order differential equations, and these differential equations are one-day differential equations independently, and what we can do is we can integrate them and apply the boundary conditions and see what their general solutions look like. So for that we'll have to first define the boundary conditions in terms of phi. So our boundary conditions here will be, so let's look at the boundary conditions and let's list them down. So our boundary condition will be phi of x comma 0. So phi of x comma 0 is equal to 0, and phi of 0 comma y is equal to 0, and the second set of boundary conditions will be phi of L comma x L comma y equals to 0, and phi of x comma w equals to 1. That's this boundary right here. So these are the boundary conditions that we have, and we will use them to uh, find our solution to the heat diffusion equation. Okay, so these are the two equations that we have, and let me correct myself. Your equation B is similar to the Finn equation, and equation A is a different equation because for the Finn equation we had a negative sign and not a positive sign. So let's look at the general solution for these equations. So the general solution for x, the capital uppercase X, will be C1 into cos of lambda x plus C2, which is the constant of integration, into sine of lambda x. So these are regular sines and cosines, and your general solution for y will be, let's write it in the exponent form, will be C3 into e to the power minus lambda y plus C4 into e to the power plus lambda y. So uh, in which case our general form or our general solution for in two dimensions, I'm sorry, in two dimensions will be your phi equals to, we'd assume that it's a phi is a combination of xx times y of y. So let's replace it with the general solution that we got for these two quantities here. So this will give us C1 to cos of lambda x plus C2 into sine of lambda x multiplied by the solution for y, which is this right here. Now we need to find the values of C1, C2, C3 and C4. So let's apply the boundary conditions that we have. So applying boundary conditions, our first boundary condition was phi of 0 comma y is equal to 0. So this gives us C1 equal to 0. Okay. Our second boundary condition was phi at x comma 0 equals 0. So that gives us C2 into sine of lambda x into C3 plus C4 equals to 0. Okay, so uh, this quantity here will not be 0, so we assume that this is equal to 0, which gives us C3 equals to minus C4. So the other boundary condition that we had was phi of x comma w was equal to 1 and phi of L comma y was equal to 0. So applying these boundary conditions, we get C2 into C4 into sine of lambda times L into e to the power lambda y minus e to the power minus lambda y equals to 0. Now the only way this equation can be satisfied is that we cannot have C2 and C4 as zeros, otherwise we won't get a unique solution. And this term here, the term in bracket, will never be zero, so our sign term has to be zero. And that tells us that, so this implies that our sign of lambda L has to be zero to satisfy this equation. Now what this means is that our lambda, or the parameter that we've chosen, must be of the form n pi by L. So if you have lambda as a in the form of n pi by L, you'll have sign lambda L as zeros, where your n are integers 1, 2, 3, and so on. So after applying the boundary conditions and combining the variables that we got, our solution for phi can be written as C2 C4 into sine of n pi x by L. That's because our lambda, we just found out that our lambda should be in the form of n pi by L, multiplied by e to the power n pi by L into y. This has to be L, minus e to the power minus n pi by L into y. Now let's combine these two variables and write them down as a different arbitrary variable Cn, and the exponents here can be represented as in terms of hyperbolic sign. So this can be written as 2 into hyperbolic sine of n pi y by L. So this makes our phi as Cn times sine of n pi x by L multiplied by 2 times sine of hyperbolic sine of n pi y by L. And let's merge this 2 into the Cn, and uh, because we have because our n here can be any integer, and for each value of n your constant will be different, we can write the general form of our solution phi of x comma y as a summation of n from 1 to infinity, and I've combined the two with Cn, so Cn into sine of n pi x by L multiplied by the hyperbolic sine of n pi y by L. So this is how your temperature distribution will look like, and we still have an unknown variable Cn, and we can use the boundary condition at x comma w equal to 1 to calculate the value of Cn. So after applying this boundary condition and after solving the complicated math, the value of Cn that we get is not a pretty looking value. It looks something like this. So your Cn will have a hyperbolic sine function in the denominator, w by L, where your n will be 1, 2, 3, and so on. So that's the value of your last unknown constant Cn. So we did this exercise so that you understand how complicated it can be to find the exact solution, or how complicated the math is to find the exact solution for a simple problem like just 2D conduction in a rectangular plate. And sometimes you may not be able to uh, get a general form or a general solution to the heat diffusion equation that you have. So uh, this exercise was just done so that you appreciate the math behind it, and you know what the general final solution or the final solution for phi of x comma y looks like.